Thanks a lot. First of all, I would like to thank the organizers for their kind invitation to this workshop. It's always a pleasure to be back here in Bern. In my talk today, I will talk about surface operators and their duality relations in four-dimensional n=2 gauge theories. And most of what I'm going to say is based on a few papers that we have written in collaboration with Billot and Frau from Torino and Sujaya Ashok and his students from Chennai, India. But actually, the whole subject builds on a very, very vast literature, some of which I'm going to refer along the way. This is more or less the plan of what I'm going to say. I will start with some general introductory remarks. Then I will introduce the surface operators in n=2 gauge theories and discuss the duality relations. And finally, I will present my conclusions. Well, the study of how a quantum field theory responds to the presence of defects in the space-time where it is defined has recently received a lot of attention from several different points of view. Defects are essentially disturbances of the space-time supported on a submanifold of it, and they can be used to probe many properties of the theory under consideration. Perhaps the simplest example of a defect is that of local operators. This is, after all, a zero-dimensional defect, local operator localized in a point in space-time. And if we put many of these operators, then we can learn a lot about the theory by studying their correlation functions. One-dimensional generalization is that of line operators, for example, Wilson lines or 't Hooft lines, which also are very useful to discuss properties of gauge theories. And then we can go on and generalize this idea to operators localized on a two-dimensional surface, and therefore the name surface operators, or in three-dimensional surface, and if we are in four space-time dimension, these are domain walls. And this list now is exhaustive if I am in four dimensions. And in this talk I will concentrate mainly on actually only on surface operators, so dimension 2. There are many different ways in which you can describe defects in four-dimensional quantum field theory. One way is to modify the path integral, the rules with which you compute the quantum observables, by imposing a singular behavior of the fields around the location of the defect. That's one way. Another possibility, which a priori is different from the first one, is to add to the theory additional degrees of freedom which are localized on the surface where the defect is extended. And if we are in a string theory context, we can think of introducing a defect by adding extra M-branes or D-branes to represent these disturbances. And there may be other ways of introducing defects. In this talk, I will concentrate on the first two ways, which look a priori different, and as I said, I will specify my discussion to surface operators. So as I was saying, surface operators in a four-dimensional theory are extended objects supported on a two-dimensional submanifold. For simplicity, I take the four-dimensional space-time to be the flat space-time, R4, and the two-dimensional submanifold where the surface operator are extended to be simply a plane R2 inside R4. So this is a picture of R4 in which the vertical red line represents the plane, the longitudinal plane along the defect, and the horizontal blue line represents the transverse plane. So in this transverse direction, the defect is clearly represented by a point. Well, these surface operators, as I was mentioning before, are actually quite important and useful if you want to really probe various non-perturbative properties of the theory, because if you introduce them in the path integral, they are sort of thermometers. They can probe properties that are invisible to the study of correlation functions, or even, in some instances, to line operators. And this was pointed out a few years ago nicely by Gukov and Kapustin. So, as I was saying, there are two ways, for my purposes, to discuss these surface operators. One, which I called the description as a monodromy defect, in which I assign the singularities of the various fields, in particular for the gauge field, around the defect. And the other is to study the coupling of additional degrees of freedom that are present in 2 dimensions, which are non-trivially coupled with the bulk 4-dimensional theory. And the purpose of this talk is to try to clarify these two ways and establish a connection, a precise connection between these two approaches. So let me start with the first one, surface operators as monodromy defect. As I was telling you before, in the transverse plane, now it's the plane of the screen, the defect is represented by a point. And if I go around that point, that defect, then I may get some non-singular behavior, some singular behavior, for the gauge field, which, if I want to preserve some supersymmetry, actually takes this form, where the theta is the angle in this plane. And these numbers, gamma 1, gamma 2, and so on, are parameters that describe the behavior of the gauge field around the defect. They can be different. The only restriction is that clearly the sum has to be 0, because I am in SUN. They can be different, and I can group them into M groups, one with N1 of them, the other with N2, and so on. So essentially it is as if the original SUN group is broken into M different components, M factors of U1 with a global U1 which is a factor out. So by giving you this formula, you see the so-called Levi decomposition of SUN into the subgroup which characterizes the defect. Now, the presence of these unitary factors and the fact that we have a 2-dimensional plane tells me that I can allow for magnetic fluxes for these UN field strength, which are of course quantized, and due to the original SUN condition, the sum of these integer numbers has to add up to 0. That's quite important because now, if I want to study the structure of the theory, inside the path integral, I have an extra option. In other words, besides the usual instanton factor with which I can weight the various topologically different configurations, which is the exponential of the second-chain class in R4 with a parameter which is the complexified gauge coupling, now I can add extra factors which measure these magnetic fluxes for these U n factors of the Levi group, which can exist in the two-dimensional plane where the defect is, with it's R2.
Yeah, but then
Yeah, okay.
it's not.
Yeah.
So you're imagining it compactified.
Yes, yes. But this just to give the idea what, just like, and with the extra parameters, one for each group of these factors. Now, so inside the path integral, I can put the exponential of this times the exponential of that. Now, it's a fact, which is not very difficult to prove, that if you compute the trace f wedge f with this singular behavior, and you use the fact that you have these magnetic fluxes, then this quantity here is the usual instanton number, which is an integer, plus a shift, which contains information with these m's, which are also integer, and those parameters which specify the singularity. Sorry? No, they go away. And therefore, the so-called instanton action, so the log of those phases that you put inside the path integral, which, as I said, it contains not only the second Chern class, but also the first Chern class, using this information becomes the usual term tau k, 2 pi I tau k, tau is the coupling constant, and k is the instanton number, plus this extra part, which contains a particular combination of those parameters with the coupling constant tau, which characterize the defect. So this is what you can put inside the path integral to distinguish the different topological configuration. You don't have any more one weight, the instanton factor, but you have actually m weights. Here you have one for each of the group, but then you take into account the overall SUN condition, so you have m minus 1 plus 1. So in total you have m factors, m different weights, and with a suitable change of variables, you can rewrite this instanton partition function in this form, in which you assign for each of these individual m-type contributions weight q1, q2, up to qm. And these are the so-called ramified instantons, and this is the so-called ramified instanton partition function. I would like to call your attention to the fact that the usual instanton weight, which is e to the 2 pi I tau, the gauge coupling, actually in this realization comes as the product of these ramified instanton weights. It is as if there are more elementary non-perturbative configurations. These are ramified instantons, which, if you combine them in a suitable way, produce for you your ordinary four-dimensional instanton. No, because what these? No, these are continuous parameters. So these t, as I will discuss later on, will play a role as phi Heliopoulos parameters. What is gamma I? Yeah, then you can take this m negative. Okay, so, I mean, there are no problems. You can always get around that. Yeah. So just like the ordinary instanton partition function can be explicitly computable, for example, using equivariant localizations a la Nekrasov, also this ramified instanton partition function can be given a very explicit expression in the various examples. by using, again, equivariant localization, or actually a generalization of this approach due to Kano and Tachikawa of a few years ago. I recall that in the ordinary Nekrasov-like calculation, you introduce the omega background, so you deform the four-dimensional space-time by introducing two parameters, epsilon1 and epsilon2, which break the Lorentz group in for space-time. And then if you introduce, for example, the vacuum expectation value for your scalar fields, you move in the Coulomb branch, then you will have the instanton partition functions, which are functions of these epsilons and these vacuum expectation values. Here, the story is similar. The difference is that you have to take an orbifold of this construction, where the orbifold is orbifold Zm, where M is the number of groups in which you have broken your original SUN theory. And this orbifold looks strange at the beginning because typically when we are used to perform an orbifold projection on the Nekrasov-like calculation, we always perform the orbifold in the transverse space, not in space-time. Here, actually, the orbifold is also affecting two of the four dimensions of space-time. Actually, those which are transverse to the defect. But apart from this, it's a very systematic procedure, and you get, at the end of the day, an explicit result for this. Once you have the instanton partition function by computing its log, you obtain information at low energy on the theory. In the limit in which the epsilon parameters go to 0, in this case you get the usual 1 over epsilon 1, epsilon 2 term, whose coefficient describes for you the prepotential, which encodes the low energy effective dynamics of the theory in 4 dimensions. But in this case, there is a subdominant piece, 1 over epsilon 1, whose coefficient in front therefore is a purely 2-dimensional interpretation, and it is the twisted superpotential, which accounts for the effective dynamics on the 2-dimensional surface of the defect. This is because in this approach, 1 over epsilon 1, epsilon 2 essentially is a rough way of writing the super volume, and therefore this explains why this is the prepotential. And 1 over epsilon 1, instead, if you look carefully also at the spinor assignments, is actually this term, d2x d theta d bar theta, so that it's a superpotential. It's a twisted superpotential. For example, in the simplest possible case in which you start with an SU2 theory, and you break into, in this case, you have only one possibility, U1 cross U1, actually with S U1 cross U1, then the result is very simple. This is for the explicit expression at the one ramified instanton level, then you can go to higher instantons without any problem. And by looking at the 1 over epsilon 1 part in this expression, you get the twisted superpotential, the non-perturbative part of the twisted superpotential.
Does this play only so in 4 dimensions, is it related to any higher derivative couplings in a vector model space, like the F-chains?
No, because the higher derivative couplings actually are the epsilon corrections in the numerators in this formula. So this is the term which survives in the epsilon going to 0 limit. If you keep also the epsilons in a...
If you put epsilon 2 numerator and denominator, that would look like some epsilon correction to the previous one.
Yeah, in that sense, yes. Now, the question that I would like to pose is, can we calculate this effective superpotential in a different way and to get some more physical intuition? And to answer this question, I think it's better to take the other way of describing the surface defect, namely as a two-dimensional object inside a four-dimensional theory. So now I will discuss a surface defect as a coupled 2D, 4D system in which the four-dimensional theory has a gauge symmetry SUN, and in it there is a two-dimensional part which, as these people described, and many others as well, actually is a two-dimensional gauged linear sigma model in which G is a global symmetry. Again, let me take the simplest example. So I take a two-dimensional gauge linear sigma model, CP1, with SU2 flavor symmetry, which is another way of saying that I have a U1 gauge theory in two dimensions with a chiral field in the fundamental of SU2. And I describe this coupled 2D, 4D system by this generalized quiver diagram in which the round node on the left describes the two-dimensional part of the theory. So it's a U1 gauge group. This is a chiral field in the fundamental of SU2. So this, from the point of view of two dimensions, serves as a flavor symmetry group. But actually, this is a four-dimensional theory. It's not just flavor, it's also a theory in four dimensions. And that's why I use this mixed notation in which it is sort with squares here with right angles, which is the usual way in which you introduce flavor, but also it's round because it's a gauge, however, in four dimensions. So let me describe this model. If I treat the SU2 just as a flavor symmetry without mentioning a four-dimensional nature, then I can go to the old literature and see that the effective dynamics of this theory is described by the twisted superpotential, which was worked out in the 80s by Dada, Di Vecchia, Davis, and others, by generalizing the anomaly argument of Veneziano-Jankielowicz in four dimensions. And this is the result in which you have a term which is a classical part, linear in sigma, that's the twisted chiral field, U1. T is a complexified phi A Heliopoulos parameter. And this is the result of integrating out the high energy degrees of freedom. So it's a result of a loop calculation. And that has the form of a sigma log sigma, which is the two-dimensional version of the more familiar sigma square log sigma term that you usually find for the prepotential in four dimensions. Here mu is the UV scale. So this is an old result. This 2 is because you have taken the trace over the degrees of freedom of the flavor symmetry. But this is a purely two-dimensional point of view. But as I was saying before, this is not really just flavor. It's a flavor, but it's also a four-dimensional gauge theory. So this SU2 has their own gauge fields with their own dynamics. And therefore, I can consider, for example, exploring the Coulomb branch of this SU2 and give a vacuum expectation value to the scalar field, which, as Ami and Hori pointed out several years ago, this induces masses, twisted masses for the sigma field. So this is a four-dimensional way of describing the theory, but still the four-dimensional theory is treated only classically because these are the classical value, classical expectation value. And to incorporate fully the four-dimensional dynamics, then what you have to do is to promote these vacuum expectation values to the full quantum theory and make, therefore, this proposal, which goes to Gaiotto, Gukov, and Seiber a few years ago, in which the quantum expectation value is taken outside the trace. So this is the effective superpotential, which describes in a non-trivial way the coupling of these two-dimensional degrees of freedom with an SU2 four-dimensional gauge theory, fully quantum. So this, if we are describing the same surface defect as before, should correspond to what I before was describing in this other language by breaking SU2 into SU1 cross U1 by partitioning the SU2 into two separate groups. And can we make a quantitative check of this? And yes, we can. And we can do this check by studying in detail this effective theory. So this is the superpotential, which I derived for you. And first of all, let me take advantage of the renormalization group equations to introduce, instead of the arbitrary ultraviolet parameter mu, the dynamically generated scale in two dimensions, lambda 1, for this U1 theory. This is the running of the Fayet-Iliopoulos, and this factor of 2 here is the right coefficient of the beta function for this term in two dimensions. So here you see the appearance of a purely two-dimensional scale from the very beginning. And we can go to the vacuum and study the stable configurations. These are obtained by computing the stationary points of dW of W. So dW d sigma equals 0 up to factor of 2 pi, so that it's more appropriate to write the equation in this form, which translates by using this explicit expression of W into this equation, which involves something in quantum in two dimensions, evaluated, however, in a four-dimensional quantum theory. And to compute this left-hand side, and therefore solve the equation, I can use now my knowledge of the four-dimensional SU2 theory using Seiber-Witten analysis, and in particular the Seiber-Witten curve for this SU2 theory. The Seiber-Witten curve for this SU2 theory is given here, in which this P2 is the characteristic polynomial, which is quadratic in this case, and it contains the four-dimensional dynamically generated scale for the four-dimensional SU2 theory, which is related to the ultraviolet scale mu and the gauge coupling tau in this way. 4 is 2 times 2, which is the beta function for SU2 in 4 dimensions. And you start seeing appearing two different scales, the four-dimensional one and the two-dimensional one, or if you like, to make a connection with the previous part of the talk, e to the 2 pi I tau and e to the pi I t, two different weights which will correspond to the various different ramified instantons. Then we can go on in the usual way. We can solve that equation by taking advantage of the resolvent for the Seiber-Witten theory and rewrite a trace of the log, the vacuum expectation value of trace log, which is what we have to compute in terms of this expression, which involves the characteristic polynomials. So at the end of the day, with the standard manipulation, your vacuum equation becomes simply this. P of sigma, remember, is a quadratic polynomial, and this is the scale. So it's a generalization of the ordinary solution that you are maybe more familiar in 4 dimensions. And you see, as I was telling you before, that we have a lambda 1 squared, but also the ratio lambda to the 4th over lambda 1 squared. Now, since it is quadratic, you can solve it explicitly. And if you do the usual expansion for large vacuum expectation values of the scalar field, then you start seeing this typical structure. So this is the solution, the profile for the chiral field, sigma in the vacuum, and the value of the superpotential on this solution, if you plug this expansion in the previous expression, takes this form, in which you recognize exactly the same expression that was obtained from the ramified instanton partition function, provided you identify, as I already anticipated, e to the 2 pi I t, with, namely the scale lambda 1 square, with one of the ramified instanton counting parameters, and the other thing that appears, this ratio, with the other ramified instanton counting parameter, in such a way that lambda to the 4th, which is the typical weight of an instanton configuration, is a product Q1, Q2. Notice also that due to the appearance of this ratio, in this class of theories, you have a hierarchy of scale, in the sense that the 4-dimensional scale has clearly to be smaller than the 2-dimensional one, because you cannot set lambda 1 to 0 unless you first have set lambda to 0. So the scales are ordered naturally in this way. Yeah, I'm strictly in the limit epsilon to 0. Then you can look at the epsilon. Sorry?
Can you find an epsilon also like this?
I think so. We didn't do that, but the expressions are there. So it would be very nice to analyze also what is the meaning of the epsilon correction to address the question that also Massimo was asking. So let me pause for a moment and make a sort of a summary of what we have seen so far. We have seen this 2-dimensional surface defect in 2 different ways. One, from a purely 4-dimensional point of view, by looking inside the 4-dimensional point of view, and from the for the singular behavior of the gauge fields, we identify the 2-dimensional structure, which is characterized by non-perturbative effects, which are called ramified instantons. And we computed the effective dynamics using generalization of Nekrasov partition function due to Kano and Tachikawa. On the other hand, from the other point of view, I started from a 2-dimensional theory, in that case the U1, the CP1 model, with flavor symmetry, and I gauged that flavor symmetry in 4 dimensions, obtaining a non-trivial structure, and the non-perturbative effects are obtained by solving the vacuum equations and computing the superpotential in the vacuum. In this approach, you naturally have the dynamically generated scales from the very beginning, which are identified in a very specific way with the ramified instanton couplings, and these ratios of scales also appears.
Is there any symmetry between the Q1 and Q2? It looks like probably there was a branch cut that you can choose a different sign.
Yeah, there are signs, and there are these kind of symmetries in which you can, yes. Actually, I will comment about that later.
Just as a comment, a couple of years ago we did a similar computation, which was to start with the full Nekrasov partition function with the ramified instanton center, and then take a limit when you decouple the block. So you tune the gauge coupling of the block to be 0. You can show that you find exactly the vortex partition function
Right.
of the defect theorem.
Yeah.
Which is similar to a little bit stronger than this.
Yeah. What I described to you in the case of SU2 actually can be generalized without any problem to SUN, and to have a generic, more generic configuration. which will correspond to this kind of quiver theories, in which, again, the round nodes are two-dimensional gauge nodes, UR1, UR2, and so on, with the arrows that denote in the usual way the matter in bifundamental representation, and which is coupled, all this linear chain is coupled to the SUN node, which serves as a flavor for this, but it also has its own four-dimensional quantum dynamics. And this corresponds to a monodromy defect in which the parameters n1 and 2, which give rise to this Levi decomposition, are associated to the ranks with specific rules that is encoded in this formula. In this case, they are growing, yes, from left to right. Yeah. Well, the ends, you can, we took them ordered as well, but this is just a matter of relabeling the various things.
You say that R's are actually convex, right? Even the secondary.
Yes, the twisted superpotential, which for the SU2 theory was quite simple, it has just a term, a classical term and a quantum term. Clearly, because you have many different contributions, it becomes more complicated, but it has the same structure as before, where again you always have these x log x contributions that come from integrating out the high energy fluctuations on the two-dimensional nodes. And finally, the last part is treated quantum mechanically in 4 dimensions. The non-perturbative contribution to W are computed from the vacuum equations, just as I discussed in the simplest example before. And you can check, and we have done these detailed checks, that they match term by term the results obtained from the localization computations using the Nekrasov-like partition functions in all details. Actually, in order to get this agreement, this perfect match term by term, there is a technical but very important point which so far I have not talked about. Namely that when in the Nekrasov-like partition function you have you want to compute explicitly the results, then you have to compute several integrals. And typically they are multiple integrals. And therefore, you have to specify the prescription with which you compute such integrals. Or, since the integrands are typically rational functions, you have to specify or to tell me which are the poles that you want to select, and therefore that you want to contribute to the result, and those which you have to reject. So this is actually what you have to do in practice in order to find the precise match. And this is what we have found. These epsilons are, as I told you before, the omega deformation parameters, but it is very useful to make an analytic continuation and give them an imaginary part, treat them as a complex number. So, in other words, the poles, the zeros of these brackets, will be points in the chi complex planes. And what we have found, but actually also other people simultaneously found exactly the same result, is for the first m-1 variables in this multiple integral, you have to pick up the poles in the upper half plane. For the last one, the one associated to the 4-dimensional node, you have to pick up the poles in the lower dimensional plane. So that means that for the blue variables, you have to close your integrals above, whereas for the red variable, the last one, you have to close the integral in the low plane. So this is actually the precise rule. If I give you this quiver-like theory oriented in this way, with the ranks increasing in this way, then to each node there is an associated chi variable in the localization integral, and the rule is that you have to integrate up in the upper plane the first n-1, and in the lower plane the last one. There is a very nice way of giving this recipe, this cookbook recipe, namely by introducing a Jeffrey-Kirwan reference vector eta, which in my convention corresponds to write this combination. If you write the Jeffrey-Kirwan vector eta in this form with the parameter psi much bigger than 1 with these signs, then you precisely get these contour prescriptions. And why I like this Jeffrey-Kirwan vector? Because these minus signs are actually correlated to the signs of the beta functions of all these nodes. Actually, they are all minus the beta functions of the Fayet-Iliopoulos couplings of these nodes. And there is an even better way of writing the Jeffrey-Kirwan vector, in which I introduce not only the sign of the beta functions, but also the Fayet-Iliopoulos couplings themselves, in which I introduce, this is the Xi1, the Fayet-Iliopoulos, the real part of the Fayet-Iliopoulos coupling for this node, and so on, which are ordered because of this structure of the quiver in this way, which is another way of saying that the various two-dimensional scales and the four-dimensional scales have this hierarchy, which is a generalization of what I told you before, lambda 1 much bigger than lambda. So it appears that our specific result can be nicely encoded in this single information from the point of view of the localization to compute the multiple integrals using this reference Jeffrey-Kirwan vector. And if you do this and you apply it one instanton, two instanton, and so on, that induces not only a specific rule to pick up the contribution and the various residues, but also instructs you to compute the integrals in a specific order in order to avoid ambiguities. And the result that you get from this calculation, we went up to 4 instantons, actually match term by term the results from the vacuum solutions. So is there a way in which we can understand this recipe, or you may ask, what happens if instead of this integration contour, I decide to integrate with a different rule? Do I get a different result? What is the meaning of that? And that's why now I switch to the last part of my talk, namely discussing duality. Yes? They are different and ordered, yeah.
But it makes sense for
1 and 2 means, yeah. It's important that they are ordered in this way so that you avoid, when you compute with the Jeffrey-Kirwan residue, any ambiguities, and you pick up exactly the values, the poles that you want. So to address these questions and make this as a broader perspective, and such a way that it doesn't look like just a cookbook recipe, but maybe has an interesting meaning, let me address the question of duality. Because we know that if we have a two-dimensional theory with gauge group UR and a certain number of fundamentals and anti-fundamentals, which I can describe with this quiver diagram. Now these are square nodes, so they are just flavors for this gauge node. Then by extending in 2 dimensions the idea of Seiberg duality, then this theory is equivalent in the infrared to this other system, which is very different because it has a different gauge group, it has the matter in other representations, as indicated by the reversal of the arrows. There is also a superpotential term which arises. So these are A and B are two different theories which in the ultraviolet use different degrees of freedom, but which share the same infrared dynamics. So they are dual to each other in that sense. And in particular, if I look at the classical simplest part of the superpotential, for theory A, this is just a T trace of sigma. This is just the classical part. If I look at the classical part of the superpotential for theory B, it is minus T trace sigma. So there is a change in the sign in the coupling constant in the phi Heliopoulos term, or if you like, in the beta functions, which is another way of saying that the arrows go in the other direction. And there is a contribution to the masses of the fundamental flavors. So if I use this basic duality move inside my more general quiver theory, I can, for example, take a general system and dualize one node. For example, this node in this oriented quiver. This node has both fundamental and anti-fundamental matter. Therefore, if I use the duality, and if I start from this superpotential for the blue theory, and I dualize this node, then I get the red theory, which is different, has a different rank. So sigma actually should be a different sigma for that, but in order to avoid the complications in the notation and use the same letter. But most importantly, the coupling here is T and becomes minus T. And due to the presence of the fundamental matter, then this term actually means that you shift also the coupling, the phi Heliopoulos coupling of the neighboring node, the one on the right. But it may happen that you have a quiver different from the ones that I had discussed so far, in which a node has only outgoing arrows, only fundamentals, and no anti-fundamentals. But the rule is always the same. In this case, both neighboring nodes are affected. So with these basic duality moves, you can take a quiver and generate another quiver by dualizing one of the two-dimensional nodes. And we did this as an example in a four-node theory. We start from the four-node quiver that I discussed before. It's m equals 4. And then, for example, I dualize this node and I get this other theory. This is a different quiver, so it uses different ultraviolet degrees of freedom. But you see the ranks of the various groups are always given in terms of the same ends. Different expressions, but the same information that I had here also is transformed into here. Then I can go on and dualize. And for example, I can obtain a quiver here, number 7, in which the arrows are all in the other directions.
What is N4?
N4. And 1 plus N2 plus N3 plus N4 is N. Big N. So you have actually 4 numbers, the sum is 1. So this is a compact way of writing. Of course, you could introduce big N minus the others. Okay, you have 3 gauge nodes in 2 dimensions and 1 of these 4D nodes. These are all different theories, and since they all come from a duality, sequence of duality, they should describe the same effective infrared physics. So they should describe the same surface operator, which, as I already indicated, should correspond to the same monodromy defect corresponding to these little n1, n2, n3, and n4, which appear all the way. For each of these quivers, you can write the W, the effective superpotential. And this is the classical part, for example, of these three nodes. And then you use the duality rules that I described briefly before. You obtain the classical part for the W of this node, and so on and so forth. And you can do also this on the quantum piece. And therefore, for each of these quivers, you know what W is. Classical, which is what is hinted here, plus quantum. And so for each of these quivers, you can work out exactly what I discussed in the originally linearly oriented quiver. Yes? That's a choice, a simplest choice. Actually, we enjoyed ourselves dualizing also intermediate nodes, and this is just for simplicity. If you do this sequence of duality, you always have linear quivers. If you started dualizing nodes here, then you have also loops inside. So it's a little bit more complicated, but completely tractable. There is no problem in that. This is just for the purpose of illustration. So for example, if you take this quiver, which is different from the one before, you have different ranks, different beta functions, different dynamically generated scales, and therefore different contributions to the various ramified instantons. And this up to signs is what we have. It's important that these n1 plus n2 or these n1 plus 2, n2 plus n3, and so on, are the beta functions associated to these nodes. So, for each of these nodes, you can work out the superpotential, find the vacuum, and check that you obtain exactly the same result from localization by using the appropriate Jeffrey-Keewan parameter, which, if you buy the prescription that I told you before, in this case corresponds to take not minus psi1 but plus psi1, because in the first node we have changed with the duality the sign of the beta function. And if you do this, then you obtain a perfect match. This is true for any other query duality, and I was saying also if you start dualizing nodes in the middle. So the bottom line is that from the localization point of view, you have a single expression, Nekrasov-like partition function, which is always the same because it represents the surface operator in that description. But you have different choices for integration contours. And these different choices of integration contours, which correspond to different Jeffrey-Keewan vectors, actually correspond to different ultraviolet realization of the same surface operator that corresponds to different quivers, which are related one to the other by the duality map. In this case, you can understand that by changing the contour of integration, you don't obtain new results, so that all theories, all contours are equivalent in the infrared. Because in these cases, where there is no matter, these are pure theories, the integrand doesn't have a residue at infinity. So if you move the contour, changing the sign in this reference vector means closing the contour below and not above. But if there is no residue at infinity, then the two things are equivalent. So the numerical result of the superpotential is the same, but the structure, the individual structure corresponding to different contours is different, and it is associated to the different ultraviolet realizations of the same surface defect that correspond to these different quivers. So I can come to my conclusions. I described the surface operators essentially in two different ways as monodromy defects. In this description, the basic information is in this set of numbers which tell me how the original SUN group is broken into various U factors. Then I introduce Coulomb branch parameters in a four-dimensional SUN. I have a ramified instanton partition function with some weights, Qi, m of them, and I can compute the effective superpotential using localization. And what I have to specify in this approach is the choice of integration contour, the prescription which leads to the result. On the other hand, if I view the surface operators as two-dimensional theories inside a four-dimensional one coupled in the way that I described, then these numbers translate into the rank of the gauge groups of the two-dimensional nodes. The vacuum expectation values of SUN become the twisted masses for the sigma fields. What were the ramified instanton parameters become the dynamically generated scale. The vacuum equations lead to the same result as localization when I solve in the way that I described, and the choice of integration contour corresponds to a choice of duality. You have an effective low energy description which corresponds to many different ultraviolet ones that correspond to different duality frames. Well, what I discussed here for this class of theories can be extended to other systems which are very similar. For example, to theories which have n equal 2 star structure, so mass deformation of n equals 4, or adding to the description that I presented matter in the fundamental representation and describe therefore n equals to SQCD-like models. In this case it's very interesting because if we put the appropriate amount of matter multiplets, then we can make all nodes to be conformal, and therefore the structure is very, very rich there. It's also very subtle because at that point the integrand does have a residue at infinity, so the issue of changing the contour is even more subtle than what I have discussed so far. It can be generalized, the entire construction, to systems in one dimension higher, so to describe three-dimensional theories inside the five-dimensional ones, maybe with coupling also with Chern-Simons like structure, and also generalize the entire thing to other groups. So far I discussed the SUN groups, but it would be nice also to generalize these and see how the details work for orthogonal or symplectic. It would be also very interesting to explore the connection with this approach with integrable models, because this kind of vacuum equations also appear in that context as well. And with this, I thank you very much for your attention. Well, I don't know if there are more general ways. This is quite general. I mean, you start from, if you want to preserve the right amount of supersymmetry, then this is, I would say, a natural way. I haven't seen personally other ways of coupling these 2D, 4D. It would be nice to explore these possibilities and see whether they are viable or not.